Welcome to problem solving session for Introduction to Group Theory. I'm Siddhibalu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 8 for this course. That is problems related to group acting on a set, group actions and its examples, orbit decomposition theorem, stabilizers of a subset, and few applications of group actions. Okay, so let us start with our first question. So let S4 acts on I4. I4 is a set containing these four elements 1, 2, 3, 4 by sigma A is equal to sigma of A for all sigma belongs to S4 and A belongs to I4. So we will discuss what action means and what it means to have, what it means when we say a group acts on a set. Okay, so then which of the following is an orbit of 4? Okay, this is the question. And first is a singleton set 1. Second option is this set 1, 2, 3, 4. That is entire I4. C is just set containing 2 elements, and option D is 2, 3, 4. Okay, we will understand properly what it means when we say, will we go through the definition of group action and what it means when we say a group acts on some set. So let us see the definition of group action. So let X be a set and G be a group. We have this two objects with us, and an action of G on X is a map. Let us call this map phi from G product X to X. Such that satisfying first that P of EX is equal to X for all X in my set X. So what does this mean? When identity element acts on my identity element E when acts on any element from my set X. So G is now acting on this set X. So the first thing we need to have is that when G acts on this X, the element again must lie in this set X. Okay, so it is like my set X is here, and when some element G acts on some element X in this set, this element must again lie in this set X. Okay, and let me call this group G. This is G, and so that X, so this is my G of X. It must again be some element of, okay, so I wrote this diagram in opposite order if I compare with the G and X here, but that doesn't matter. Or let me just change it. And when I say G acts on X, it goes to some element, which is again an element in my set X. Okay, so that's how it should be. And it says that if when my E, the identity element of my group G, acts on any element of X, that must fix that element there itself. So if E here is acting on X here, then E of X must be equal to this X again. So whenever my identity element acts on any element of set X, it must be equal to X again. And the second property is phi of G, comma, phi Hx. Okay, this must be equal to phi of GHX. Okay, this must be equal to for all X in X and for all G, comma, H in my group G. So what it says is, note that this is again some element in X. So it is like, so it, if my phi is some G, comma, if I call this, if phi of H, comma, X is Y, which is again some element in X, then what I want is this phi of G, comma, Y must be equal to phi of this GH, comma, X. And this Y was my phi of HX, we know here. Okay, so this is the property we must have to declare that G is acting on X under this map phi. So there are many ways of defining an action on a given set, and we will see some examples where a same set G, same set X, but the way G acting on X changes. So whenever we answer the questions related to group action, please make sure you are uh, properly understanding what action they are talking about. So this is, and in short, so just for shorthand, often this G, comma, X is denoted by just Gx. So it is like this G acting on X, or just now I'm expressing it in a dot, or just sometimes we just write it with juxtaposition. Okay, so that's how. So we have to see how this S4 acts on this I4. So S4 is acting on I4. Here my phi is from X S4, comma I4 to I4, and any element of G is acting on elements of X. Okay, so what it does is, we take an element, suppose my so it's like sigma, comma, A is going to sigma of A. So for example, if I take 1 comma 2, my sigma, and A is suppose my 3 belongs to I4, then sigma of A will be just 3, because this sigma of 3 here is just 3, because under this 1 transposition, 1 2 transposition is of this, is this. Here sigma of 1 is 2, sigma of 2 is 1, sigma of 3 is 3, and sigma of 4 is, okay, sigma of 4 is 4. So that's how the action is defined. And now what they are asking is, I hope the action is quite understandable. So note that even though sigma 4 has like this 4 elements here, I mean, it's kind of tuple of 4 or cycle of 4, and I mean, it is bijection of 4 objects to 4 objects, and my I4 is just a set, and it when sigma acts on I4, it acts on an element of I4. And and again it is giving me some element of I4. So so the way sigma acts on different elements of A uh, changes. For example, sigma of 1 comma 2, and if I take A is equal to 2, then sigma acting on this 2, or yeah, let me just write sigma acting on 2 is sigma of 2, and sigma of 2 is 1 now. Okay, so for each s element in for each element in S4, the way it acts on I4 is different. Okay, so I hope you understand what I'm trying to say here. And now they are asking us that if this is the action, then what is the orbit of 4? Okay, so let us understand what orbit of a set means. So if, again, this is a definition, if let G be a group and acting on a set X. So when we say that G is a group acting on a set X, we already assume that there is underlying a group action given to it. Okay, and if X is some point in X, then the set Gx. So this Gx is G acting on X. So there is some underlying group action and my G is acting on X. Gx, or let us write phi Gx such that G belongs to G. So it is collection of all the phi Gx such that G is in G. So what we do is we are fixing now X, and okay, so this is the set is of the point, no, is called the orbit of the point X, and it is denoted by, I mean, we will be denoting it by, or I will denote it by uh, OX. So this suffix X is the one which is signifying that orbit of it is. So orbit is something we define for element from set X on which the group is acting. We do not have orbit of some element in G. We have, so it is like if this is my set X, this is my group G, okay, and X is point here, and each element of this G is acting on this point X, and then this X takes different so this G, then this X becomes now Gx. So this was my X here, it acts on, G acts on it, now it becomes Gx. Okay, and now each and every such element of G acts. For example, if this is G1, G2 acts here. If this was G1, suppose it goes to G2, X. This is my G2X. And now this, all the collection of all these images under this map phi when G is acting on this X is the orbit of X. It is also sometimes called as trajectory of X. So it is like, if I look at it, so X will always be there. So it is like some, so if you want to look at it, you can look at it where all this X goes in this set. So for example, when X acts here, this might be my G1X, this might be my G2X. Okay, so you can imagine it as how the X is moving when G is acting on it. Okay, so we have to find now this, we have to find orbit of 4 now. Okay, and then orbit of 4 is what? It is phi of g x g4. We want to find it for 4 such that g belongs to S4. And note that the moment I get all the elements of I4, I don't need to check furthermore. So for example, I want, so it this is subset of I4, right? So the moment I get all the elements from I4, I can declare it that orbit will be the entire set I4. We don't have to then go ahead and check it for each and every element uh, uh, of G. So for example, if I take this identity element in S4, this one is mostly denoted by S4, then sigma, this sigma, if this is my E, right? So E of 4 is just 4, right? So 4 belongs to my orbit anyway. Because see, for any OX, X always belongs to this. Okay, so for any, let me write this here. For any X in X, X always belongs to OX because by definition itself, we know that EX is X, right? Phi EX is X. Identity acting on any element, it fixes that element. Okay, I mean identity acting on an element, we get the resultant element in X to be the same element X again. So again, E4, so 4 was anyway, so 4 is in my O4. And now if I take this transposition, E is equal to 3, 4, not E, sigma 1 is equal to 3, 4 in this S4, then sigma of 4 will be what? It is 3. This is sigma of 4, but 4 goes to 3 in this transposition. Okay, sigma 1. So this is 3. So now from this, I have 3 belongs to O4. Okay, and we can take now this sigma 2, which is 2, 4. So I'm just choosing elements which can give me different images of 4 as much as possible, so that I can find like how many like what are the elements which we get when 4 acts on it. Okay, so sigma 2 of 4 is to this sigma 2 of 4. And under this transposition, this is my transposition, and sigma 2 is 2, 4, and it is this 1 is fixed, 3 is fixed, 2 is now going to 4, 4 goes to 2, and sigma 2 of 4 is now 2. So my 2 belongs to this O4. Okay, and similarly, I will take this one 4. I just want to see how 4, what images 4 takes when G acts on it. And then it will be sigma 3 of 4, and it is 1 now. So all 1, 2, all the elements 1, 2, 3, and 4 belongs to my O4 under this group action of S4 acting on my set I4. Okay, so this so the answer is this set 1, 2, 3, 4. We just checked. Okay, so that's how. So and if you, so now let me give this as an exercise. So check that for each element X in I4, OX is this set 1, 2, 3, 4. You can check this. You can try to find this sigma i's and sorry, and see that you can send any element from I4 to any other element of I4 using some element from group G. Okay, and now the next so I hope this question is okay and you do not have any doubt. If there are any doubts, uh, please write it in the discussion forum if you see this and if you have any doubt. Uh, and we will now go to the next question. And it is that question 2, that let G be a group and my X is again G. So it is now G is again acting on G. So my X is set G. Then uh, which of the following is are true? Okay, the first option is the map Gx going to Gx is an action of G on G. B, the map G comma X going to Xg inverse is an action of G on G. And let me just shift this. G comma X going to Xg is an action of G on G and T. None of the above. Okay, so these are this is some action how G can act on itself. So G is a group and X is, so when we talk about group action, this X could be any set. So these are some actions, these are some actions which we often use to uh, see how G is acting on itself. Okay, so this is when we write this G into X, note that this X is again some element from my group G. So Gx is well defined here. So again, I'm writing here, note that Gx is, I mean, the multiplication here, the multiplication Gx is well defined here as X belongs to X. Sorry, X belongs to G. And this Gx is group multiplication or this group operation, whatever we have defined on G. Okay, so similarly for Xg inverse and Xg, this is just elements from group G itself and we are multiplying them. So we have to check now whether they form G, the way this map P is defined, whether it is actually a group action or not. So first thing we have to check whether so for A to check that, let me write this in this way, going to G such that Gx going to Gx is group action. Okay, that's my thing to check. So first is we have to check whether P of E comma X is X or not. So what is phi of E comma X? it is E into X, right? But E is group identity and X belongs to G. So this is anyway X. So note that since E is an identity of G and X belongs to G, therefore we have this EX is equal to X. And second property was for all G comma H in G, for all X in X, we must have phi of G comma PHX as phi of GHX. So let us first calculate what is phi of G comma phi X. In our case, it is phi G of HX, just the multiplication of group multiplication. And this is phi, and this is what? G into HX, that is GHX, right? I mean, we have this associativity of group operation. And what is my phi of GHX? It is GH into X. And these two things are equal. Okay, so this multiplication is actually a group action. Therefore, G comma X going to GX is a group action of G on G itself. Okay, so I hope this one holds. Now we have to check for the second one. G comma X going to XG inverse. B part. To check whether phi G comma G, sorry, G cross G to G such that G comma X going to, what was it? XG inverse. XG inverse is a group action. And again, we have to go with these two conditions. That is, let X belongs to X, then phi of, that is my G again here, phi of E comma X is X into E inverse. But E inverse is again my E. Okay, so this is X into E. And that's E because E is the identity of the group, and XE is equal to X is equal to AX. We know this. So this is true for any element X in X, which is G here. And now the second property is let X belongs to X and G comma H belongs to my G. Then phi of G comma phi HX is phi of G comma phi HX is my XH inverse from the given, as per the given action. Okay, and what is now G acting on this XH inverse? This is XH inverse into G inverse, right? So this is X into H inverse G inverse. This is my action. This is how the definition of this given action, this is the definition. We are not doing anything special here. And now I need to check what is phi of GH comma X. It is what? It is X into GH whole inverse. Okay, and we know that it is H inverse G inverse. Okay, so I hope you all know this. GH inverse is H inverse G inverse. You can check this if you don't know. Okay, check if you don't know. I mean, we all know this, but still, if you don't know, it's good to check. And so this phi G of phi HX is definitely equal to phi of GHX from the definition, and we just checked, and this is true for any given x and any GH were arbitrary. Therefore, this phi, so this G comma X going to X, G inverse is an identity, oh sorry, is a group action of G on G. Okay, so these two properties we checked. So this second one is also a group action. Now let's go to the third one. Now my GX is going to XG. Okay, so now this C to check again. This piece from G cross G to G, and this G comma X is going to X into G. And we have to check whether this is group action. I mean, this might look very trivial, but it is very important to see how G acts on itself. Okay, and the first one is again, let X in X. So what is phi of E comma X then? It is X into E, which is X because my E is identity, and that's not a problem here. But now the second one. So let X belongs to X and G comma H belongs to my G. Okay, so this you can do, and then phi of G comma phi HX will be what? Phi of G. Now HX is XH. The order is reversed, and now it is XH into G, right? So this is what? X into HG. And now I need to check whether this is equal to this phi of GHX. But what is phi of GHX? It is X into GH. But is this equal? So is this XHG equal to XGH? No, right? This need not be true because G is given to be just any group. We do not have any information whether this G is abelian or not. Okay, so this G here needs to be an abelian group in order to have this as a group action. Okay, so always understand this. So is this always true? So answer is no. This need not be true if G is not abelian. And you can try this with this example as well. If you take S4 acting on S4, and we know that S4 is not commutative. And in that case, if you have this as your action, then it would not be. Try with, you can, for counter example, try with any non-abelian group. Okay, so example, we can take this S4, which we know, we have seen many examples where we use S4 as a counterexample at many places of where we wanted something to be non-abelian. Okay, so not even S4, you can also try this with S3, and you can check that this is not a group action. You can take any two transposition. Maybe you take 1 2 3 and 1 3 2, something like this, and try to. I mean, I think this, if I'm not mistaken, this is 1 going to 3, 3 going to 2, and let us check this. If my x is just identity, and so my phi g is 2 3 and h is 1 2 3. I don't know whether these two elements commute or not, but let us try. So this gh x will be just this 1 2 3, and 1 is going to 3, 3 is going to 2, 2 is going to 3, 3 is okay. There is some problem. 2 is going to, wait, 2 is going to, 1 is going to 3, 3 is going to 2, 2 is going to 1, 1 is going to 1, and 3 is going to 2. Sorry, 3 then will go to 3 itself. So it is 1, 2, the transposition, and phi of x comma, no, not x, it is g comma phi hx will be phi of g and h into e. So hx is just h into 1, right? So 1, 2, 3. 1 acting on 1, 2, 3. That is just 1, 2, 3 again. And 1, 2, 3 is now will act on 2, 3. Not act, but it is just multiplication. And you can check that 1 is going to 1, here 1 is going to 2. And 2 is going to 3 here, and 3 is going to 1. Okay, these two elements commute. Doesn't matter. But you can check with some other elements, and you can see that this it's in this is not in general true. You can take two elements which do not commute, and you will see that GH is not equal to HG, and the ultimately we get that this is not true in general. This is not equal, and therefore this is not, let me write here, this is not a group action if G is not abelian. Okay, and this is anyway it's gone. So please check this explicitly with some examples where you choose two elements which do not commute from S3, and get the counter example and so on. Okay, so I hope this was clear so far. If not, please let me know. And now the next question, it is related to the similar kind of question, and it is, oops, no, question 3. That let G be a group, and again my X is G. The map P from Gx to X defined by G comma X going to G inverse X is, we have to choose which of the following statement is true. Is never a group action. B is always a group action. C, that it is a group action if G is an abelian group. And D, that is none of the above. Okay, so we have to check in what conditions this GH is a group action. Okay, so is this always so? See, under this action, for any x in X, phi of Ex will be what? It is E inverse X, that is Ex, and I get X again. So that's not a problem here. E acting on some element is not a problem under this group action. So we have to check about the second condition. That is, we have to check whether this phi of G phi Hx, whether this is equal to phi of GHX or not. Okay, we need to check this. So if this holds, then what we will have? This phi of G phi Hx is what? It is H inverse X. It will be phi of G comma H inverse X, and then this will be G inverse H inverse X. Right? This will be my phi G phi Hx. And what is phi of GHX? It will be GH inverse X, but that is H inverse G inverse in general. Right? So if phi is a group action of G acting on itself, then this G inverse H inverse X must be equal to H inverse G inverse X, right? And since we are in a group, we can multiply by X inverse on both sides, and we are left with H inverse G inverse is equal to Hg. And this is what? This is Hg inverse, and this is Gh inverse. And then we get that Hg is equal to Gh. You can do the required, what I can say, required modification. Okay, and you will get what is required here. So GH must be equal to HG then. So if this needs to be a group action, then I must have HG is equal to GH. And this must hold for all H and G in my group G. So that will give me that it is group action only if G is abelian, right? Because it if I mean it is true. I mean it is it see we need to have this, right? So if G is abelian, then this H inverse X will be equal to this H inverse G inverse X, right? If G is abelian, this is for all X, G, H in G. So this one is anyway not true, that it is never a group action. Under a abelian group, this will always be a group action. But the question is, will this always be a group action? No, because the moment I have some non-abelian group, then when it acts on itself under this action, then it need not be a group action, because this in general, these two need not be equal. Okay, and that will give me that this phi here is not a group action. And so when it is a group action, it is a group action when G is abelian. Okay, we just arrived at the condition by assume that phi is a group action. So therefore, if G is abelian group, then we get that this Gx going to G inverse X is a group action. Is this okay? And this one is anyway we can discard. Any doubts here? If not, then we will move to next question. Yeah, we will see how we can go about this question. So let Ge be a group of order p power n for some prime number p acting on a set S. Okay, so G is acting on some set X. They have not explicitly given the group action here. They are just saying that G is a group of order p power n for some prime p, and it is acting on this set S. And let this SA is equal to set all those S0 is all those element A in S such that GA is equal to A for all G in G. Then they are saying that which of the following is true. Okay, wait, is this correct? No, this is wait. This they have defined like GA such that all those G in G such that GA is equal to A. Okay, so we have fixed the A and then which of the following is true? And A that GA is a then GA is a group of G or not. Okay, this is the question that G is a group of order Pn for some prime number P acting on the set S. Then we have to check whether this GA, let A in A, and this GA is defined like this. Then we have to check whether this GA is a group or not. And for this, we do not even need this order of G. Let us just first prove that. So this GA is called the stabilizer of the group. Okay, and we have to check whether this GA is a subgroup of G or not. Okay, so let us check that. So we have to check whether it is a subgroup. So first of all, we have to check whether identity belongs there or not. So E definitely belongs to GA because we know that under any group action, this E into A is A by the definition of group action. Okay, and now we have to check for all G comma H in G whether GH inverse belongs to, sorry, in GA whether GS inverse belongs to GA or not. Okay, so note that G and H belongs to GA. So what does this imply? That GA is equal to A and HA is equal to A. Okay, and if I multiply, I have HA here. So if I pre-multiply both sides by H inverse, what I get is H inverse HA is equal to H inverse A. And now this gives me H inverse A is A. So therefore, the moment H belongs to my GA, its inverse also belongs to my set. So therefore, this G, so G belongs to my GA and H inverse also belongs to my GA. So now I have to check whether this GH inverse belongs to GA or not. But GH inverse into A is what? G into H inverse A, right? And that is G into, from here I get A and GA is anyway is equal to A. So therefore this GH inverse belongs to G. And this was true for all my G and H in G. So this stabilizer is actually a subgroup of, so this is not at all needed. G be a group. Acting on set S, let A be in G. So this GA is definitely this for A in G, sorry, A in X actually, A in S. For A in S, GA is equal to all those G in G such that GA is equal to A is called the stabilizer of this element A. So it is collection of all elements of group G which stabilizes the element A. Okay, so what was the problem? Like, what is not clear? This section, I assume I could not hear the notification of your message. Could you please, sorry, where was the doubt? Is it in this section or the previous one? Or that no is for you do not have any doubt? Okay, so let me just go through the question again. We just have to, so this G is a group acting on some set A, S, and they have defined this set GA. It is called as stabilizer of a set, and we are just checking that stabilizer of a group is actually forms a subgroup of group G. And we know for to check the group subgroup for any group, we first have to check whether identity of the given group belongs to that set or not. And for all G and H from that set H, whether this so we have for group to form, we have these multiple conditions, right? That it should be closed under addition. For every element, there must be identity must exist and inverse must exist, right? And closed under multiplication and so on. So all those conditions of G being subgroups are taken care using this property here. And we are just checking for any G and H, if I take from this set GA, whether GH inverse belongs to GA or not. When I say GH inverse belongs to GA or not means this is G into H inverse. Okay, these are two. G is one element, H inverse one element. And I'm just checking this. Since G and H both belong to GA, from GA I get A. HA is this. I'm pre-multiplying by H inverse to get this. And this G and H inverse. Now I just need to check this, whether this holds. And since H inverse belongs to GA, it gives me A, and G into A again gives me A. And therefore this GH inverse belongs to G. Okay, so I hope this is okay and you do not have any doubt here. Is this okay now, or there is still some doubt? Okay, so let us move to now next question. If there are any doubts, please, you can unmute and ask if there is any doubt. Otherwise, we will move to next question. Yeah. Okay, so let G is equal to Sn and X is equal to Rn for X is equal to x1 to xn in Rn. And this sigma, this is question I think 5. This sigma, yeah, and for sigma belongs to Sn, we define this sigma x is equal to x sigma 1 x sigma n. And then G acts by the map sigma x going to sigma of x. So let A belongs to R and P be this element A comma A, all the tuples, all x, all A, all the entries are A in Rn. Then the number of elements in the orbit of P is this is the question which we need to answer. So first of all, let us understand how the action. So earlier the first question which we try to solve, I4, the element on which the group or the set on which the group was acting had only 4 elements here. But now this is completely different action. So this is G acting on Rn, again giving me some element in Rn. Earlier, when G was acting on that I4, it was giving me some element from that set I4. It was just an integer. Okay, but here, when G acting on Rn, I'm getting again a tuple Rn. And how it is acting? So, for example, it says that if sigma is in G and my x1 to xn is in Rn, then it goes to sigma x1 to x sigma n. So just for understanding, if n is 3, I'm choosing 3 here, and let 1 going to 2 going to 3 be in S3, and my x be, let us take 4, 5, 6, or let us take even something root 3, root 7, root 9, doesn't matter. Not root 11. Okay, this in my Rn. I can take anything, any tuple in R3, and how it goes that sigma, this 1, 2, 3, is now acting on this root 3, root 7, root 11. And how it goes? It is going to x sigma 1. Okay, so x sigma 1. So 1 is going to 2 here, right? So this is my x. So this must be my x sigma 1, that is 2, x sigma 2, that is 3, and this x sigma 1, sorry, x sigma 3, that is 1. So this must be x2, x3, x1. And here this is my x1, x2, x3 from the original. So it is root 7, root 11, and root 3. Is this okay? That's how. And this is again my element from Rn, that is R3 here. That's how this group action is defined. Okay, and now we have to find all the, so P is this, so they have A is some element in R, and this P is all those, is filled with this A. Each component is just entry A, and we have to check like what will be the size of orbit of this element here. So I hope you remember what orbit was. It is all those x in x such that x is equal to gp is equal to x for all. It is just this phi of, wait, it is phi of gx for all g in g. So in this, here this is op, so this is sigma p for all sigma belongs to Sn. This is the set which we are talking about. We have to find how many elements are possible here. Okay, so since A since P is just A, doesn't matter whatever permutation you apply. So if sigma is in Sn, then sigma acting on P will be what? It will be P sigma 1, P sigma n, right? But each and every entry of this P is just element A. Okay, so note that P sigma I is equal to A for all 1 less than equal to I less than equal to N. Okay, so doesn't matter whatever sigma you choose, it will always be this element A. So therefore the only element in OP, that is orbit of this element, it just is P, that is again this A. Okay, so the number of elements in this orbit is just 1. Okay, so the answer is 1 here. The only element belonging to that orbit is 1. Any doubts here? Not, then let us move to next question. Let G is equal to R plus. So this is R under addition, standard addition, and X is R2. And the map P is from Gx to X defined by P of T comma XY. Let me just write this here. Is equal to ETX comma Y. So we are just multiplying this E power T in the first coordinate, and we have to check whether it is a group action. So we have to check whether this is true or false. The phi given here, we have to check whether this is a group action. And let us start with checking those two conditions. And here my group G is R plus, and in R plus, the identity element is 0 element. So let X comma Y belongs to R2, and we have to check this phi of 0 comma X comma Y, right? So then this is E power 0 into X comma Y, and E power 0 is again 1, and I'm getting X comma Y. So therefore, for all, and this XY in R2 were arbitrary. So therefore, for all X comma Y in R2, I have P of 0, which was my E here, of X comma Y is X comma Y, and therefore, the first condition is satisfied. So this first condition is satisfied. Now the second condition. So let T1 comma T2, or let S comma T belongs to R, right? Yeah, S comma T belongs to R. That is my G. Okay, G. Let me write it explicitly. So then phi of S comma phi Tx is equal to P of S comma E power Tx. Wait, this is X comma Y here. And this is phi of S comma E power Tx comma Y. And again my xy and in R2. This is phi of S. And again, this is E of S E power Tx comma Y. But this is what E power S plus Tx comma Y. And now phi of St, but R plus we are talking about. So this multiplication is actually addition. So this is R plus T comma X comma Y. So this is E power S plus T X comma Y, and this is exactly equal to this phi of S comma phi of T comma XY. So therefore this phi of S comma phi of T comma XY is equal to phi of S comma S plus T comma xy, comma x, comma y. Okay, so therefore, this both the conditions are satisfied, and therefore, this is true. The given action is indeed a group action. Now, let us move to the next question, question 7. For which of the following numbers n there does not exist a simple group of order n? Okay, so they are asking about simple groups. We will define what a simple group is. Option is 14, 38, 26, 62. Okay, so the, let us see the definition of simple group. A group G is called a simple group if the if it does not have any proper normal subgroup, and that can also be written as that is the only normal subgroup of G are this identity element and G itself. Okay, so any doubts here? Note that G, when we say that G being normal, the G as a group itself being normal, we need not have G to be abelian or anything. Okay, the definition of G being normal is just this, that we say H is normal subgroup of G if G inverse is contained in H. Okay, this is the only condition we need to take care of. And in case of G itself, this for G subgroup of G. So I'm just looking at G as its own subgroup. This G inverse is anyway always contained in G inverse. Sorry, it's always contained in G. This is just group being closed under multiplication. Okay, so we do not need to have G to be abelian group in order to consider G itself as a normal subgroup. Okay, so now this is the question, and to answer this, we will use this theorem, that this result, or I would say, if you do not know, please know this, that for any group of order PQ, where P and Q are distinct primes. Primes is enough. Wait. Are primes, then any group, then G is not a simple group. That is, there exists a normal subgroup of G. Okay, so this is the statement which we will use. So you can prove this statement, and if you do not know how to prove this, you can raise the query in discussion forum and we will try to answer that. But this you can assume for now, that if G is any group and P and order of G is some product of two distinct primes, then it can never be simple. So when we are asked this here, we just need to check whether it is product of two primes or not. So for example, 14 here, it is 2 into 7. It's product of two prime. So by this previous theorem, it can never be simple. Okay. The proof is actually since it is product of two elements, sorry, two prime numbers 2 and 7, we choose an element of order P or Q, or whichever is lesser, and we quotient the group. So there exists an element of that order, right? So the order of a group is P into Q. So there exists an element of order P in that group. Okay, so we take the cyclic group generated by that element and then we take quotient by it. And the resultant group will be isomorphic to some group of order Q, and it will be cyclic, and we can get that the group which we quotiented is normal and so on. So you can try to go like prove the statement yourself. And so this is product of two primes, and so by this result it can not be a simple group. And in fact, the maximum, let me write it with the result itself. The there exists a group of a normal group of order Q in G. Okay, if we take P less than Q. Okay, and similarly, so by that result, we will have some group of order 7 which will be normal in G. Similarly, for the group of order 38, so this does not have a simple group. Similarly, 38, it's 19 into 2. So it will have some normal subgroup of order 19. So again, this will be my group of this will not be a simple group because it will have a normal group of order 19. Similarly, for 26, it will be 13 into 2. Let me just write it here. 2 into 13, and here it is 2 into 31. So these are all groups of order 2 into p kind of structure, and this p greater than 2, and it all contain a normal subgroup of order p here. So here everything is 2 into q, and it has we have a normal group of order q. And in fact, we also have a result which states that if G is a group of order 2m where GCD of 2 and m is 1, that is m is odd, that is m is odd, then G has a a normal subgroup of order m. Okay, and you can check this. And in fact, not even for this, there is also generalized result which also states this, that if G is a group of order 2 power n m where 2 does not divide m, then again G has a normal subgroup of order m, and so once it has some normal subgroup of order n, G is not a normal subgroup. Oh, G is not a simple group in that case. Okay, so there will be a group of order m which will be normal in G, and that will give us non-trivial subgroup of G that is normal, and G need not, and then G is not a simple group. Then we can conclude that G is not a simple group. Okay, so I hope this much was I hope so this was okay. So let us now move to next question. This is related to the previous question which we solved about Sn acting on Rn. So let G, this is question 8 I feel. Let G is equal to Sn and X is equal to Rn. And for again the same for sigma belongs to Sn, we define sigma X is equal to X sigma 1, X sigma n. Then G acts on X by the map as we defined earlier, sigma x is going to sigma of x, and let a not equal to 1 be a real number, and p is this 1, 1, 1, and rest are all a's. Okay, and let me just write this here. In Rn, then the number of elements in the orbit of P is, and the options are 3n, n cube, n minus 1, n minus 2 by 3 factorial, and D is none of the above. So we have to just see like how this P, what is the orbit of P is all those phi sigma P such that sigma belongs to Sn. So let us try to see this using simple example. And for example, let us do it in for S4. Let P be this 1, 1, 1 and A. That's it. This will be my P. And let us see how many elements this P can take. How many, what I can say, when when sigma acts on P, what are the possibilities I get for this? So if I take this 2, 4 or 1, 4 in S4 acting on P, then 1, 4 acting on P will be just 1, 1. This is, let me call this here. This is my P1, P2, P3, P4. Let us denote it like this. This will be my P1, this is P4, and this is P sigma 3. Here, sorry. This is P sigma 1, P sigma 2, P sigma 3, and P sigma 4. So this will be P sigma 1 is 4, P2, P3, and P1 here. So P4 was my A, 1, 1, 1. Okay, this is my first element, which is different. So for now, P belongs to OP. This element here belongs to OP. And do you have any more possible choices for this? For example, if I take for 2, 4 belongs to S4. So note that why I'm taking 4 in every transposition is because this is the, what I can say, this is the only position where A is there. So see, one commuting among each other will not give me any different element here. So I just have to check what are the possibilities of this A moving in this P. Okay, so look at it as permutation among this tuple here. With, and that's how S4 is acting. So S4 is my permutation group anyway. So it is like I'm just shuffling these coordinates of P and seeing what are the possible outcomes I get as I make S4 act on this. So when I take 2, 4 in S4 and I make it act on this P, then it is sigma P sigma 1, P sigma 2, P sigma 3, and P sigma 4. And this is the last time I'm writing this. Then I will just directly write So P1 is P1, P2 is P4, P3 is P3, and P4 is P2 as per this. Because note that sigma of 2 is 4, sigma of 4 is 2, and I get this. P1 was 1, P3 is 1, P4 is my A, sorry, yeah, this P2. And P2 is again 1. So this belongs to OP. Okay, and for again 3 comma 4 belongs to S4. This 3 comma 4 acting on P will be just permutation of this 3 and 4. And 1, 2 remains as it is. So this is 1, 1, A comma 1. And note that these are the only 4 possibilities I will get. Okay, because all the rest, this one shuffling among itself will not help us anyway. So, and what is the number then? It's 4. So cardinality of OP here is 4. And what gives me the number 4? So 3 into n was 4 here. So that's anyway not holding. So note that here n is 4. So this anyway is not true. This anyway is not true. And what is this? This is 4 into 3 into 2 divided by 3 into 2 into 1. And I get 4 here. Okay, so this is the answer which we have. But we just saw it, I mean, we just try to saw this for this particular example of S4. But I hope you understand how it works because see, instead of this 3, if I have something like this, wait, yeah, that's correct. And so instead of this 3, if I had something like this, so if you can check this, if my P or P is of this form, 1, 1, 1, this K positions, K positions, or K, okay, K positions, and now I have A here. This K is my less than equal to n, doesn't matter. Equal to n will not create any harm. And you can check that in this case, orbit of this P is n minus 1, n minus k by k factorial. Okay, you can check this. You can also like try to see this using examples and also try to prove. Because what this is, we have this k once and we are trying to shuffling uh shuffling them among these n positions. And the rest are all A's and the other ones are just ones. So it is like how many positions I can place this one. So, and this is the formula which we all know for that. So if you have any questions related to this, please raise those questions in discussion forum. We try to answer those as much as possible. And let us move to now next question. So I think this is question 9, that let G is equal to GLNR and X is equal to SLNR, then we have to check this is true or false, that the action of this phi from G comma X to X given by AB A inverse, sorry, A comma B going to AB A inverse is an action of GLNR on SL and R. Okay, so we have to just check again those two conditions, which we have in order to check the given action is a group action or not, or given map defines a group action or not. So again, let so my again let me write here. My G is GLNR and X is SLNR. I hope you all know what is SLNR. So GLNR is all the invertible matrices, or the way we can also have is that A in M and R such that determinant of A is non-zero, and SLNR, this is just one of the way of writing this, is all those matrices such that determinant of A is 1. Okay. So now, first of all, note that this action is well defined. That when I do this, note that P is a well defined map. I mean, before checking whether it is a group action or not, we first need to see whether this is a well defined map or not. And it is because, note that what is phi of A comma B? It is AB A inverse, right? It is AB A inverse. And what is determinant of AB A inverse? It is determinant of A, determinant of B, and determinant of A inverse, right? And determinant of A inverse is, it will be some whatever. Determinant of B, we definitely know it is 1 because B belongs to SLNR. And this is of determinant of A whole inverse. So this entire thing becomes 1. And the moment I have determinant of AB A inverse 1, this imply that AB A inverse belongs to my SL and R. Okay, so this is well-defined map. So now let identity element belongs to GLNR. We know that under multiplication, this is my identity in GLNR. And what is phi of IN comma B? Let B belongs to SL and R. Okay, so it will be IN, B, IN inverse, right? And we anyway have identity here. So IN into B, IN inverse is IN again. And I get resultant matrix as B. And this definitely belongs to SL and R because determinant of, I mean, this is what we need to check. So phi of identity acting on B is B for all B in SL and R. So the first condition holds. So now let us go for the second condition. So let A belongs to my GLNR and B belongs to SLNR. I need two elements, right? So let us take A, comma C belongs to GLNR and B in SLNR. So phi of A, comma phi of CB will be what? It will be phi of A, comma CBC inverse, and phi of A will be A CBC inverse A inverse. Okay. And what is my phi of ACB? It is it is AC into B into AC inverse. But since we are in matrices, we have this C inverse A inverse, and that is exactly equal to what I have here, right? These are equal. So second condition, therefore phi of A comma phi CB is equal to phi of ACB, and therefore P is a group action. And this group action, which we defined here, uh, is not only there for matrices. In general, so in general, for G in G, and sorry, for in general for group G and the set X again equal to G, the action defined like P of defined P of G comma G to G given by as P of G comma X going to X G X inverse is a group action and is called as conjugate group action or just conjugate action. So this is also, you can check that it follows from the same argument which we gave here. Okay, it will be identity. So for first it for Gx, it will be for identity into X, it will be Ex inverse, and again this will be Xx inverse and wait, this is Gx G inverse. Yeah, X as it is, sorry. G X G inverse. So it is X E inverse, and this will be X. And for the other, if I take G phi of H comma X, it will be the same which we have, that is Hx H inverse, and here it will be Gh X H inverse G inverse, and here again phi of Gh will be Gh Gh inverse, and this will be my Gh H inverse G inverse from the inverse, and these two will be equal. And that's how I get that this is a group action. And this conjugate group action is used uh, a lot when we talk about theorems, which we will be seeing in next week mostly, for orbit stabilization theorem and all other, in many proofs for group actions to see its orbits and all other things. This group action is heavily used, and okay, it you can understand this properly. This is a group action, and it is used heavily. So that this was just one special example where we proved that it is a group action. Okay, and so let us see a few more examples which, yeah. So let us check this. Wait. Yeah, for the orbits we will see. So let us check this question. Wait. Mm, this question 10. So let G be, if we'll have time, G be GL to R and acts on R2 through A comma V, going to this normal multiplication, and we have to check what is the orbit of first. E1 is equal to 1 comma 0, and B, E2 is equal to 0 comma 1. Sorry, we have to check this. So this is, we are in GL2R. GL2R is a set of all invertible matrices, and it is acting on AV. So this action does not require it to be. I mean, what I'm saying here is, no, wait, yeah, we need it. So this P is from G comma R, GL2 comma R cross R2 to R2, such that matrix here comma V is going to just matrix multiplication normal here. So if I have something like A, B, C, D, just matrix here in GL2 and here XY, then this simply goes to AX plus BY and CX plus DY. Okay, and we have to check what is the orbit of this 1 comma 0 here. So if I have this A, B, C, D, some matrix in, and they have already given that it's all acts on R2. So we are assuming that this actually uh, is giving me orbit of R2 already. I mean, it is the action. So this, I'm not checking that this is action. This itself is giving me the action. And I'm just checking now what is the orbit of this element 1 comma 0 in this. So when I multiply this by 1 0, I get this A into 1 plus B into 0 and C into 1 plus D into 0. So this is basically A comma C. So what this does is, This gives me the first column of my given matrix. Okay. So, and I now need to find what is the orbit of E1. So when I say orbit of E1, it means orbit of, let me just write here, orbit of 1 comma 0 is all those x comma y in R2 such that, no, it is all those, and what is your guess for this now? Because I'm getting here a comma c. So this is just a comma c such that a, b, c, d, this belongs to GL2R. And so can we say that this is whole of R2 minus this 0 comma 0? Because see, if I take any x comma y in R2 minus 0, 0, okay, so what it will be? Then I can choose this matrix xy here. Okay, and since one of them is non-zero, right? So what I will do is just see, so if since x comma y is not equal to 0, 0, this imply either x is non-zero or y is non-zero. So what I will do is I will just take this a to be x, y, 0 and x here. And in that case, determinant of this matrix will be x square. And since x is not 0, assume x non-zero. Since x is non-zero, this x square will be non-zero. And so determinant of A will be non-zero because determinant of A will be in this case x square, right? And therefore this A will belongs to GL2R. And when I multiply this A with 1, 0, it, as we saw earlier, it will give me the first column. Similarly, if 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 x is non-zero, then this. If y is non-zero, then I can choose A to be this matrix x, y, y 0. And here now, since y is non-zero, determinant of A will be minus y square, and this will again be non-zero. And this then matrix A will belong to my GL2R. And then this will imply that my sorry, this x comma y A into 1, 0 will be x comma y. And if you do not even have to do this, note that we are in R2. Okay, the dimension of R2 over R is 2. So if I consider this, so this is like I need to find some linearly independent element in R2 other than this xy. So if I take this xy, choose any element which is not a linear combination of this xy. Okay, so whatever you want, choose any element, x dash y dash, which is not a linear combination of this xy, and this xy into x dash y dash, determinant of this will never be 0. Then determinant of this is non-zero, and therefore this xy, this x dash y dash will belongs to this GL2R. And that's how when I take this xy, whatever linearly independent other column you chose, into this 1 0 will be my first column xy, and this will belong to my O10. So therefore the orbit of this 10 is whole R2, the R2 minus 0, okay? Therefore orbit of 10 is R2 minus this 0, 0. I hope this is understandable. And similarly for B part, B is what? My E2 they have chosen is 0, 1, and see how this acts on again any matrix. It is AB. If I take this, this is 0, 1, and this is giving me B into 1, C into 0 plus D into 1. And this is again BD. So it is giving me the second column. So again, in this case, it will be the whole R2, because if we for any xy in R2, we can take this x dash y dash xy, choose x dash y dash in R2, which is not a linear multiple, it's not a linear combination of xy, and determinant of this x dash y dash xy will be non-zero, and this x dash, the similar argument which we did, but now we are doing it for the second column. A will belong to this GL2R, and thus this x dash y dash xy into 0, 1 will be xy, and this I was choosing non-zero. When I do this, this is non-zero, okay? 0, 0 is not possible, because no, what is this? This is giving me column of a matrix in GLNR. So no matrix in GLNR will have a column as a 0, 0, because then determinant will be 0 and it won't be in GL2R. So it is, if at all it is giving me column of GL2R, it has to be some non-zero vector in R2, or non-zero element of R2. And that's how I get this xy. So therefore, again, this O of 0, 1 is entire R2 minus this element 0, 0. And if this helps you, if you have any doubt related to this, please write it in the discussion forum, or yeah, and we will try to answer those. And if not, and now we just saw this for two elements, 1, 0 and 0, 1. What about any? So do this as an exercise, or check that if I take any non-zero xy in R2, then what will be this orbit of xy? And try to see how it works. Okay. And note that for order of this, sorry, not order, orbit of this element 0, 0 is just 0, 0. Okay, because orbit of 0, 0 is just 0, 0. You can take this because whatever matrix you take, it will always give me 0, 0 as a vector. So, okay, so notice that when we define this action, we do not need that this is whole, it is defined on whole of R2. And when we got the orbit for this element E1 here, which was 1, 0 and 0, 1, I got R2 minus 0, 0. And but to define the action, we do not need it to be R2 minus 0 and so on. Okay. And this is well-defined action. Okay, you can check this. If you are not convinced, check that this AV going to AV is a well-defined action, or not well-defined action, is a group action. Is a group action of GL to R on R2. Okay, if you do not take those two conditions, check condition 1 and 2, which we have been checking. Okay, check and you will see that it is a group action. And please try to uh, do this for exercise. It will be a good exercise for you. And I think we are already over time now. So I hope this was helpful. If you have any doubts, please feel free to raise those in the discussion forum. And we will meet next time, uh, next week, same time. If you have any doubts, uh, please come up with your doubts for the next lecture and we'll try to solve it. Thank you.